everybody, welcome back. In this video, we are going to be talking about basic rules of differentiation. Recall from our previous video that the definition of a derivative involves a limit. The definition of our derivative is f prime of x equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. So we're trying to compute slope of tangent line. We're seeing what happens when points get really, really close together, and we're computing a bunch of secant lines getting really, really close together. And that gives us our tangent line. Okay, so that's the definition of a derivative, and we did a few examples of computing computing derivatives using this limit definition. And they were kind of long and clunky. So this is a great definition for theory. Anytime you want to prove something about a derivative, really, you use this definition. But this isn't a proofs course. This is an introductory calculus course. So we're going to make our lives a lot easier and start talking about some rules for differentiation that make things simpler. Just like how we have our limit laws that make computing limits simpler. Alright, so let's introduce some notation. In fact, I have the space down there. I'll put it down there. Alright, d dx of f of x is the derivative of a function f with respect to x. Alright, again, this is not a fraction. Think of that as like its own entity that can only travel all together. Like maybe plus or divide, right? You can't cancel the two dots and then divide symbol, right? You have to leave it as it is. Same thing with d dx. This is not 1 over x. This is d dx. Okay, so d dx of f of x is the derivative of f with respect to x. That is d dx of f of x is equal to f prime of x. It's useful to have this notation d dx of f of x because sometimes, again, you might be working with multiple variables or just a different variable. Hey, maybe your independent variable for a problem is time instead of x and you want to use t's. Okay? Then you talk about d dt of f of t. Same thing, just different variable choice. Okay, with that out of the way, let's start talking about some rules of differentiation. The first one, all of these are theorems, is called the constant rule. And what this says is the derivative of a constant is 0 for any constant you want. So for all real numbers c, the derivative with respect to x of c is 0. Okay, let's prove that. To prove it, we're going to use the limit definition. So let's let f of x equal c. Then f of x plus h is also just c, right? There's no x's to plug things into, so we're just left with our constant. So f of x is c, f of x plus h is c. So f prime of c, or not f prime of c. So d dx of c is the limit as h goes to 0 of f of x plus h minus f of x over h. That's the limit as h goes to 0 of c minus c over h. So limit as h goes to 0 of 0 divided by h, but 0 divided by anything is just 0. Limit of 0 is 0. And that concludes our proof. Mathematicians filled in squares at the ends of proofs. It makes us feel fancy. It's the same reason we use chalkboards, actually. There's no other good reason to use them over whiteboards, but it makes us feel better about ourselves. Okay, so this rule states that the derivative of a constant is 0, and I proved it here, but you might be like, that's Greek to me. Let's see visually what's going on. Here's a function defined by a constant, f of x equals c. And let's note that at any point we pick on our function, the tangent line is just that line back again, which has slope 0. And therefore, the derivative is 0 everywhere. Right? If the derivative at every point is 0, then the derivative as a function will be 0. Okay, so that's our first rule of differentiation. Any constant you see a derivative via, instantly 0. So that's helpful. For an example, let's let f of x equal pi squared plus 4e to the 27th power minus 6,421. Ridiculous number. I wouldn't compute that in a million years. F prime of x is just 0. Derivative of a constant is 0, no matter what the constant is. Okay? Write down this side. I'm going to erase it for our next rule. Okay, here we go. It's nice not having to stand around as people write things down. I can just be like, pause the YouTube video, and then you can. Okay, our next rule for calculating derivatives is going to be called the power rule. And yes, it's worthy of the name since it's a very powerful rule indeed. So, what is this power rule? The derivative with respect to x of x to the nth power is equal to n times x to the n minus 1 for all real numbers n. So no matter what the number n is, the derivative of x to the n is just n times x to the n minus 1. So you can think of it as it pulls it down in front and then it subtracts 1 from the exponent. Okay, let's prove it when n equals 1. The general case is kind of hard to prove, but looking at it in at least one case is probably helpful for us. So, let's let f of x equal x. Then, let's view x as x to the first power. Then, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h, which is equal to x plus h minus x over h, or sorry, not equal to that, equal to the limit as h goes to 0 of x plus h minus x over h, which is the limit as h goes to 0 of h over h, limit as h goes to 0 of 1, which is just 1. But 1 is equal to 1 times x to the 0th power. Which is exactly what we wanted it to be, right? You pull the 1 in front and subtract 1, you get 0. In fact, the constant rule is just a special case of power rule, but we'll state them separately. Okay, your book has the case when n is equal to 2, and as I said, the general case is difficult, so we won't prove it. But this makes computing derivatives much, much simpler. Really quick. Let's let f of x equal x to the 7 over 2 g, and this is divided by 7 halves, g of x equal to x to the 4th, h of x equal to 1 over x squared, and k of x equal to the 5th root of x. With just the power rule, we actually have enough to compute all those derivatives. So let's find f prime of x, g prime of x, h prime of x, and k prime of x. Okay, well, f prime of x is equal to, we have x to the 7 halves, so we're going to pull the 7 halves in front, times x to the 7 halves minus 1, 7 halves minus 1 is 7 halves minus 2 divided by 2. So we have x to the 5 halves power. Boom. And that is f prime of x. Right there. Again, directly applying power rule. 7 halves got pulled in front, and then we subtracted 1 from it. Let's do g prime of x. G prime of x is going to be equal to, okay, pull the 4 in front, and subtract 1 from the exponent. 4x cubed. How about h prime of x? Well, let's rewrite. H of x is 1 over x squared. And you might be like, but that's not in the form of the power rule, that's not in the form of x to the n. Okay, you're right. But we can make it in the form of x to the n. Using our exponent rules, this is x to the negative 2nd power. So, h prime of x is going to be, pull in front, negative 2 times x to the negative 3. And that's a valid way to write our answer. We could also write it as negative 2 divided by x cubed. Again, using our exponent rules. And that's what I'll choose to write it as. That's h prime of x right there. K of x is kind of the same idea. If k of x is equal to the 5th root of x, using our rules of radicals, this is x to the 1/5 power. So, k prime of x will be 1/5 times x to the 1/5 minus 1. 1/5 minus 1 is negative 4/5. And you could rewrite that with radicals if you wanted. Be the 1 over 5 times the 5th root of x to the 4th. Okay, yeah, so power rule, very helpful for computing derivatives. But we have a couple more derivatives that make things, or sorry, a couple more rules that make things even nicer. Okay, so the first rule talks about how derivatives play with scalar multiples. And the long and short answer is they play nice. Mostly because limits play nice with scalar multiples. So, the derivative with respect to x of a constant times a function is just a constant times the derivative of a function. So scalar multiples pull out of derivatives. That's real nice. The proof is in your book. If you want to try doing it on your own, I would commend you for it. Okay, other quick theorem. This is known as the sum rule and talks about how derivatives play nice with addition and subtraction. It's exactly what you would want. The derivative with respect to x of f of x plus g of x is the derivative of f of x plus the derivative of g of x. And the same holds true for subtraction. Great! That's awesome! Because now, and also your book, I think, might have the proof of this, like, later on. It's not too hard to prove. It's just follows directly from the limit definition. But yeah, so these two theorems, together with the power rule, are now enough to let us compute the derivative of any polynomial that we want. So let's do it. And polynomials are a very useful class of functions, so now we know a bunch of useful derivatives. Where did my good chalk go? There it is. It dropped. Okay, let's let f of x equal 5x cubed minus 7x plus 4. And let's find f prime of x. Okay, so finding f prime of x, we're taking the derivative with respect to x of 5x cubed minus 7x plus 4. Okay, even though we've only stated the sum rule for two functions, it works for as many as you want. So we can split up across these plus or minuses. So this is the derivative with respect to x of 5x cubed minus the derivative with respect to x of 7x plus the derivative with respect to x of 4. Okay? So this to this, yeah, there's not a lot of grade space inside. This is the sum rule being applied here. Okay? And now what we can do is we can pull out the 5 and the 7 from these derivatives using this theorem about scalar multiples. So this is 5 times the derivative with respect to x of x cubed, and that's by scalar multiples, minus 7 times the derivative with respect to x of x, same thing, and then derivative of any constant is just 0. So that's just plus 0. And this is by the constant rule. I recognize that that might be hard to read, but it is written. Okay, so we have 5 times derivative with respect to x of x cubed. That's just 5 times 3x squared, and that's by the power rule, minus 7 times derivative with respect to x of x. So this is x to the first, 1 pulls in front, and we're left with just 1 plus 0. Cool. So this will be 15 x squared minus 7. And that is our final answer. F prime of x is 15x squared minus 7. So I wrote all of this out. You should do this at least for the first few times, right? Because this is showing your work and because it'll help you really get a grasp of what can I and can't I do with derivatives. Let's do another example. Let's let y equal 12 divided by x squared plus 3 halves times x squared minus x. And let's find dy dx. Alrighty. Well, dy dx is equal to, okay, let's rewrite. This is 12 times x to the negative second. Applying all of our rules at once, this will be 12 times negative 2x to the negative 3 plus 3 halves times 2x to the first minus derivative with respect to x of x is just 1, right? Aka 1 times x to the 0. I guess in fact this should also be within the parenthesis. Alright. Which evaluates to negative 24 over x cubed plus x minus 1 using our rules of exponents. Okay, or sorry, plus 3x. Man. 3 halves times 2 is 3, not 1. Okay, if that was a little quick, let's do it out step by step. Gonna erase this side. Alright, so the play-by-play of this one. We have this 12x to the negative second rewrite. Let's take that for granted. We're trying to find the derivative with respect to x of 12x to the negative second plus 3 halves x squared minus x. Okay? Well, according to the sum rule, we can split this up as the derivative with respect to x of 12x to the negative second plus the derivative with respect to x of 3 halves x squared minus the derivative with respect to x of x. Now let's pull the scalar multiples out. So using our rule for dealing with scalar multiples, this is 12 times the derivative with respect to x of x to the negative second plus 3/2 times the derivative with respect to x of x squared minus the derivative with respect to x of x. Right? That one leaves alone. There's no scalar to pull out. Okay, now we can apply the power rule. And we're left with 12 times negative 2 x to the negative 2 minus 1, which is negative 3. Plus 3/2 times, pulling the 2 in front, gives us 2x to the first. Minus derivative with respect to x of x, just 1. Again, you can think of it as 1 times x to the 0. Which is precisely equal to this thing, using just algebraic manipulation. Alright, so those are some basic rules for differentiation. If you're comfortable, feel free to jump from here to here. I would like you to at least show this one step in between. If you're not comfortable with that, that's okay. Go step by step. See which rule you're using each time, and it all shakes out nicely. The more familiar you get with these things, the faster they go. And we'll be able to do more examples together as a class on Thursday as well. All right, have a great rest of your day, guys.